Hello dear students. So, in continuation to our discussion of plasma motion when it is treated like a particle, we have considered various configurations of electric and magnetic field, primarily uniform and static. So, in today's class, we will try to understand how the plasma will move or a charged particle will move when it encounters a magnetic field which is not uniform in space. So, this discussion is called as the gradient drift. So, what it means is that if you consider plasma as a composition of electrons and ions, and if these electrons and ions are subjected to a magnetic field, which is, let us say, B, which is along a particular direction, which is changing with respect to space, changing with respect to space. So, we are still retaining the variation of the magnetic field with respect to time as it is. That means, magnetic field is not changing with respect to time, it is constant with respect to time, but the magnetic field is, let us say, a particular direction is not 0. What it means is that it is having a gradient, or the amount of magnetic field that you can find at different points along a particular axis will be different. Or if you draw unit surface area, the number of flux lines that you can expect to be crossing this unit area will be different at different places. So, which means that the magnetic field is having a gradient. So, you see this in this example that I have drawn. You see, if you have taken this to be a unit surface area, there are two magnetic flux lines which are passing, and if you are going along this z direction, you will see more flux lines are passing through this unit surface area. So, we can say that since the magnetic field is defined as the number of flux lines, flux per unit area, we can say that the flux is increasing or the magnetic field strength is increasing. So, our motivation in studying this or in deriving this is going to be able to derive an expression for the trajectory of a particle or an expression for the generalized drift in a situation when the magnetic field is changing with respect to space. So, for this we have now invoked what is called as the magnetic field is no longer homogeneous, it is inhomogeneous. So, the situation is inhomogeneity. So, inhomogeneity is defined to be in the length scale of L. That means, the magnetic field is changing over the length scale L, or within the limit, within the distance limit less than L, the magnetic field can be assumed to be homogeneous. So, there are no changes in the magnetic field. So, and we will make one more assumption saying that, let us say, if we have RL, which is the radius of gyration of a particle in a magnetic field, we can define RL to be m v perpendicular by qb. So, in order to match these two things, what we will say is, we will say that the RL, the length scale over which one particle gyrates, will be much in comparison to the capital L. If L is the length of inhomogeneity, so RL will be much less than L. That means, as long as the particle is gyrating in a single orbit, the magnetic field can be assumed to be a constant within that gyration length or the diameter. So, this is one important assumption that we make in order to proceed further. So, let us say the basic conditions are the magnetic field is inhomogeneous in space, then we have it is static in time. We can say just static. Let us say we say that it is static in time. So, let us consider a coordinate system, and we can, with that reference, we can see how the magnetic field can be described. So, this is your choice of coordinate system. So, you have x, y and z, and now you consider the magnetic field to be changing like this, which is, so let us say these are the magnetic flux lines. So, what I am drawing are the magnetic flux lines that are coming out of the page. So, you always remember this reference or how the magnetic flux lines are denoted. If you see a cross, if you see a symbol like this, you always remember that the magnetic flux lines are coming out of the plane of the surface. If you see something like this, the magnetic flux lines are going in. Okay. So, one thing that is very clear from this figure is that the flux or the number of flux lines coming out of the surface per unit surface area is increasing in the positive y direction. So, this is the direction of the gradient del B. What is del B? Gradient always indicates the direction in which the physical quantity is increasing, right. So, this means that it is evident from the figure itself that the magnetic field is increasing as we go in this direction. So, let us put some references here. Let us say 1, reference 1, reference 2, reference 3. And we will denote the magnetic field itself to be in the z direction. So, the magnetic field is in the z direction, its gradient is in the y direction. I hope it is very clear, right. So, there is, we do not talk about electric field as yet. So, this is the situation, and if now plasma comes and experiences this magnetic field, plasma which is assumed to be made up of electrons, ions, neutrals, but neutrals will not have any effect when they will not experience any effect when they see a magnetic field. Now, we have to understand how this magnetic field can influence the motion of electrons and ions. So, we can see that the magnetic field strength changes from 1 to 3. So, if you bring the expression for RL, it is going to be m v perpendicular by qb. So, as the magnetic field strength increases, the radius of gyration will decrease. So, that means that as the particle moves from 1 to 3, its radius of gyration will start decreasing slowly, right. So, let us say how we can include all this. Okay. So, we assume the magnetic field to be Bz along y cap, and the gradient of magnetic field is, let us say the magnitude is del B, which is across j cap. All right. So, now as per the generalized drift, let us recall the generalized drift. If you have the generalized force F, which can give to a generalized drift, which is F cross B by QB square. So, if the particle is acted upon by a generalized force, which can be anything, The resulting drift that the particle will experience is given by this expression. Now, since we have considered a non-uniform magnetic field, we will make an approximation which is suitable to make it convenient for the mathematical derivation. So, we have dou Bz by dou y can be approximately equal to Bz by L, or what this approximation says is that the rate at which the magnetic field changes with respect to the distance along y is approximately equal to the ratio of magnetic field, the strength of magnetic field over the distance L, where L is the length scale of inhomogeneity. The length scale of inhomogeneity precisely defines the distance parameter over which the magnetic field changes. So, you can reasonably consider that before that length scale, anything shorter than L, any distance shorter than L, the magnetic field can be assumed to be a constant. So, we are working at that approximation limit where we say that the magnetic field is of course changing, yes, but it is not changing over this very small distance which we call as L, right. So, this implies that Pz by L will be much less than Pz by RL, because we have used the fact that RL is much less than L. So, we can write RL times dou Bz by dou y will be much less than P. So, this is a very important relation that we will need further. So, having established this relation between the length scale of inhomogeneity or the rate at which the magnetic field changes and with respect to the radius of gyration, what we are going to do is we have a limit within which the magnetic field is changing or after which the magnetic field is changing. So, what we will do is we will expand the magnetic field in that limit. Okay. So, magnetic field, if you have, let us say, if you can write magnetic field is equals to, is going to be B naught plus y dou B by dou y plus so on. What is this telling us? It is telling us the magnetic field can be obtained by a Taylor expansion around that length scale of inhomogeneity. So, we are going to neglect all these higher order terms because they will speak of a variation which is not actually present in the picture or which is very, very small and can thus be neglected. So, neglecting all the higher order terms, we will take the magnetic field to be of this. Okay. And why are we taking this magnetic field? Because we are interested in evaluating this expression. F is equals to E times E plus E times V cross P. Why is this expression important? So, we have already learnt the importance of this expression. This is the Lorentz force. So, this tells us the effect of the electric field and this tells us the effect of the magnetic field. But what we have known so far is that the magnetic field is going to be of this form because it is changing with respect to space. So, this term which is assumed to be 0 earlier is not 0 in this picture, right. So, this is where we have to substitute this magnetic field and get some expressions, right. So, we will use a result which we already know. For example, so we know in the case of a uniform magnetic field, in the case of a uniform magnetic field, what we know so far from the earlier discussion is that the position can be written as RL sin omega ct, y is equals to plus minus RL cos omega ct, whereas the Vx, the x component of the velocity is V perpendicular cos omega ct, Vy, the y component of the velocity is plus minus V perpendicular sin omega ct. Now, the conclusion or the important aspect concept that you have to understand from this is that when the magnetic field is uniform, this is how the position coordinate x and y can be written. So, where RL is the radius of gyration, omega c is the gyration frequency, V perpendicular is the perpendicular component of velocity, right. So, these two x and y, let us say they exhibit a circular motion with a radius RL. So, if you take x square plus y square, you will get RL square. So, what does it mean? It is moving in a circular path with RL as the radius. Now, most importantly, as long as there is no electric field, the particle will keep gyrating at a fixed position if it does not have any component of velocity which is parallel to the magnetic field. So, if you have V parallel, and if this is the magnetic field, let us say if this is the magnetic field will make the particle move in this circle, because the way it is drawn on this does not appear to be a circle, it is revolving in a circular motion. So, if it has a parallel component of velocity which is non-zero, then the particle will keep moving in this direction and at the same time execute a circular motion. But if it is not there, it will just keep gyrating in a fixed orbit, right. So, now let us say we use this formula, which is the force. Since there is no electric field, we will write E times V cross B, right. So, we have V, the velocity, written as Vx, Vy, Vz, the B as written as 0, 0, Bz, right. Evaluate this curl, what you can get is Fx is going to be Q, Vy, Bz. So, if you want to know how I got this, it is straightforward actually, minus Q, Vx, Bz, Fz is equals to 0. How did I get these relations? This can be written from, let us say we take the curl I Jk, Vx, Vy, Vz, 0, 0, Bz. What am I doing? I am just trying to evaluate the curl. So, if you break this, let us say I cap times this one, Vy, Vz, minus 0, right, minus j cap 0 minus Vx, Vz, right, plus k cap times 0. So, this is the x component that I have written here, is the y component I have written here, 0 is the z component. So, this is I have written this just for the sake of clarity, so that you may not think how did I get these relations, right. Now, the task is I have these expressions for Fx, Fy, Fz. We know what is B, Vy, Vx from these expressions, that let us say we call this as, so this expression is an important expression, let us say we call this as 1, this as 2, this set of equations as A and this set of equations as B. So, we can use set of equations, let us say B, into this, and we will rewrite, as a matter of fact, when we write A and B into this, we can rewrite it as Fx is equals to q Vy Bz, which is equals to q V perpendicular sine omega c t. Since Bz has to be written as B naught plus y dou Bz by dou y. You see here? So, Bz has to be written as per the expression 2. So, what we have made use of is, we have this set of equations as C. So, substituting equation B and 2 in C, we get this, and which can be further simplified as q V perpendicular sine omega c t times B naught plus minus, using for y RL cos omega c t dou Bz by dou y. Then we have Fy as minus q Vx Bz. So, substituting similarly, we can write minus q V perpendicular cos omega c t times V naught plus minus RL cos omega c t dou Bz by dou y. Fz is 0. Now, what I want you to understand is that generally when a particle moves in a magnetic field, it experiences force which changes its direction, only direction. But here what you are able to see from these three expressions or the two expressions is that the particle is not just experiencing a force because of B naught, it is also experiencing a force because of the way it changes with respect to the magnetic field. You see, plus minus. Plus minus is there to accommodate the polarity of the charge, but otherwise one thing is clear, we have an additional term appearing in the force expression which conveys the message that the particle is experiencing additional force because of the gradient or change in the magnetic field. So, Fx, Fy, Fz are the magnitudes of the forces, right. Now, what we are interested to see is that, let us say if a particle is gyrating in one orbit, let us say, what will be the average amount of force that the particle experiences within one gyro orbit. So, if you write F, the force as a non-zero force Fx component Fy, Fz, what we are interested to see is what is the average amount of force that the particle experiences in one gyro orbit. The moment it completes one gyro orbit, what is the average amount of force? Okay. So, we have to evaluate, if you want to find out the total average force, we have to evaluate what is the average force Fx, what is the average force Fy, and what is the average force Fz. Right. How do we characterize one gyro orbit in terms of distance or frequency, anything like that? So, let us say we write average force component Fx as q V perpendicular B naught average sin omega c t plus minus RL sin omega c t cos omega c t dou Bz by dou y. You see this, what I have done is I have taken sin omega ct into the bracket and written an average of all the parameters. So, when you take an average of during one gyro orbit, how will the things change? So, we know from simple mathematics that average of sin omega ct is 0. Average of sin omega ct between 0 to 2 pi, right? One gyro orbit, 360-degree rotation is 0, and at the same time average of sin omega ct cos omega ct is also 0. So, that means fx, average fx is 0. What does it mean? It means the particle is not experiencing any average force in x direction over one gyro orbit. Fine. Let us see the story with Fy. If we take the parameters that are outside the bracket into the bracket, we can be able to write qv perpendicular b naught cos omega ct plus minus RL cos square omega ct times dou bz by dou y. So, average Fy, so average of this cos omega ct is 0 and average of cos square omega ct is half. So, Fy average is equals to minus q v perpendicular RL by 2 dou pz by dou y, and Fy is this Fz is anyway 0. So, what have we realized? We have realized there is one non-zero component of the force along the y direction, the other components are 0. This is a very important result. Let us just try to understand this. Okay. When the particle is moving in a magnetic field which is changing with respect to y, the particle will experience an additional force just because of the change of the magnetic field, not because of the magnetic field, but an additional force because of the change in the magnetic field. So, you see here Fy seems to be dependent on dou bz by dou y, and at the same time Fx is 0 and Fz is 0. So, if you take the original magnetic field configuration that we have started with, what you are able to see in this picture is that as the particle moves in this direction, it is experiencing a force in the y direction. So, Fy, average Fy. So, what is the total effect of this? So, if you take the expression for the generalized drift, which is 1 by q F cross B by B square. Because of this additional force, we will write F is equals to 0, average force that the particle experiences within one gyro orbit is equals to q v perpendicular RL by 2 dou bz by dou y comma 0. How did I get plus minus minus plus? Because there is a plus minus here, right? So, when it comes out after this, I should have actually written plus minus. Instead of plus minus, I should have written minus plus, because if this minus multiplies this plus minus and we have this minus plus. Now, let us evaluate the drift. Because this drift is because of the change in the magnetic field, we will say 1 by q, since Fy is the only non-zero component of the force Fy cross B by V square. Since this is due to the gradient in the magnetic field, I will write gradient as this velocity as the gradient drift velocity is equals to 1 by q minus plus 1 by q q V perpendicular RL by 2 dou Bz by dou y along y cap, because this is Fy cross Bz. The direction of Bz is along z cap, but the gradient of B is along y cap, Bz square. Or in simple terms, we can write it as minus plus V perpendicular RL by 2 Bz dou Bz by dou y. Y cross z is x cap. V perpendicular RL by 2 Bz dou Bz by dou y along x cap. Right. So, this is the expression for the gradient drift velocity. You see, what do we have? We have a velocity which is appearing in the left hand side. V perpendicular is the perpendicular component of the velocity. You have V, this is the perpendicular component, this is the parallel component. V square is equals to square root of V perpendicular square plus V parallel square. So, now the important point here is this velocity is along x cap direction. It is not in the z or it is not in the y. Let us put some reference here. The reference is, you have this is the z cap and this is the x cap and this is the y cap. The choice of coordinates is that we are taking like this x, y and z. Now, this is the direction in which the magnetic field's gradient is there, and this is the direction the magnetic field is present. Now, the drift is perpendicular to both these, and this is the direction of the drift. So, this is what you have to actually understand. Of course, this is very clear since the beginning, because we have a cross product and we can only expect the gradient drift to be perpendicular to both the physical parameters which you are involving in the curl operation, right. So, this is where we stop. So, this is an expression for the gradient drift velocity.